Okay, hello everybody. Welcome to the first ISGC seminar in 2025. First of all, wish you all a happy new year. And I'm happy to announce Rainer Spurzem as today's speaker. He did his PhD, or as we call it in Germany, Dr. Reanat at the University of Göttingen in 1988. Then in 1996, he did his Habilitation at the University of Kiel. And since 2003, he was a professor at the University of Heidelberg, where he is now retired. In addition, he is since 2009 also affiliated with the National Astronomical Observatories at the CAS in China and the Kavli Institute for Astronomy and Astrophysics at PKU. First of all, thank you very much for agreeing to give this talk. The stage is yours. You're muted. Rainer, you're muted.
Yeah, sorry. Once again, I will start. It happened here. I just had here a disturbing bar. Actually, I move it away and then I got muted. Now you should be able to hear me, right? And
Yes.
Once again, thank you very much, Torben, for inviting me to this really widely distributed international seminar. And yeah, this is for me, I'm not sure, I'm not very familiar with the audience here in the seminar. I'm mainly an astronomer, astrophysicist, dynamicist, theoretical, and also doing a lot of computer simulations. And the topics of our astrophysical computer simulations are nuclear and globular star clusters. I will just introduce in the beginning a little bit more what these objects are. And it so happens that in these star clusters, naturally, we get very compact objects, black holes, neutron stars. And when we want to follow their dynamics accurately, it's necessary to deal with the relativistic dynamics of these objects. And since this is not something like in great detail where we do full numerical relativity, it's rather like a huge Newtonian system which we have and a few relativistic objects. And it is a most convenient and suitable, as I hope to show you a little bit, to do this with post-Newtonian dynamics, which is basically adding or correcting the Newtonian gravitational forces between particles, correcting them in order to take into account relativistic effects. And so this is what we are doing already for many years for our simulations. And Torben asked me in this talk to highlight a little bit the way how we are using this post-Newtonian dynamics. So I tried it. It's I hope it is not too mixed, too chaotic. So because mainly our results, our papers are astrophysical papers, and I try to add a little more material from the underground, so to say, how we deal with the relativistic and the post-Newtonian dynamics. And let me add also one more thing. It's I'm not a relativist in that sense. Yeah. So all of this relativistic dynamics, that is something we are using, we are taking published work, citations, and we are implementing it into our large computer simulations. Yeah. So questions certainly, as I think is usual in your seminar, anytime, just shout. So I'm happy to answer questions. So basically, we have 3 chapters: the little introduction and leading over to globular star clusters, then nuclear star clusters, which is a little bit more different topic and will be less detailed maybe, but with some potentially very interesting perspectives with regard to relativistic dynamics. And codes and hardware, and then the final summary. Codes and hardware is something, it's important, it's our tool, our instrument, but I understand it's not the main topic here, so I will just try to keep it short or jump over, depending on where we are in time. Now, a few words to the institutes, these three affiliations, just in case maybe it's not to everybody very well known. University of Heidelberg, that is, let's say, my main German affiliation for many years. And this is a small German town, but has a lot of astrophysics. And you see here the three institutes, the Rechen Institute, Computing Institute, which I am coming from. There's this Theoretical Astrophysics Institute in the university and an observatory. Then there are also Max Planck Institutes. And maybe most interesting if you have somebody looking for a graduate student position, there's a graduate school, an international organized graduate school with every year deadlines in November. Now it has just passed. It's called the IMPRES, the International Max Planck Research School. And we have every year, we have a large number of applicants from all over the world. And it is jointly carried and organized by the university and the Max Planck Society. Then, yeah, this is our institute, the Rechen Institute, just for the history. It's a very old institute. It used to compute calendar data. It was also one of the first institutes having a computing center and a big supercomputer in 1964. Yeah, just if you are interested, ask me about that. The building does not look very historic. It's just a new building. New means 60s of previous century. Yeah, so this is then the Kavli Institute, probably some of you may know. It's the Kavli Institute of PKU, and its founding in 2008 actually that brought me to China. The interest actually in this new international, at that time, new international institute with very diverse faculty and postdocs and students. And it so happened at the end, because I needed a large supercomputer for my research, that finally I landed at the National Astronomical Observatory of Chinese Academy, where we actually started something which is called the Silk Road Project. That is here, and it is a computational science project, and it is, in that sense, a computer is one of the many instruments in NAOC, supported by NAOC. Typically, they have telescopes of all kinds. I don't go into the details here. So yeah, this is how I landed at NAOC. Now let me start to make the link between astrophysics and gravitational waves with a very old plot, which I always like, and I just like to put it in my talks occasionally. It's from a review from 1978 about the potential gravitational wave sources in the universe. And there are here 4 scales, and the right-hand side is the one which is most common now today. That is a frequency of gravitational waves from, yeah, we have here -4, so less than 1 hertz, millihertz here, the -3. Yeah, so this was today what we say is the LISA frequency regime. Here we have 1 hertz and 2 and a kilohertz. So here we come to what is today the ground-based domain. And on the left-hand side, we have this here in the orbital time of a binary. And then we have here in the x-axis the energy of the bodies, or the luminosity on the top here. Yeah, and I just don't want to discuss all objects. I just want to here highlight the 2 objects I will be talking today. So one is here, which is called globular cluster holes, black holes and globular clusters, which are running here from 100 to 10,000 solar masses. And these objects, this is what we will find in our simulation, and where I will discuss somehow how from in our simulations we estimate what kind of gravitational wave events we get from them. Yeah, and down here we have galactic nuclei and quasars, and there we have the more massive black holes. Yeah, 10 to 5, 10 to 6, 10 to 7, 10 to 8. And also there we have one branch of our group actually working on these objects. And all of this is it's typically these lines here. We think about binary black holes. Yeah, so the gravitational wave sources which we have in mind here are binaries of these objects. Yeah, this in this mass range. Yeah, there are other objects here, the formation, the whole bursts. You see here the bursts, but this is, I will not discuss this today. Yeah, so this is just how we start, and let's start with a globular cluster. So what's a globular cluster? A globular cluster. This is just not a new picture. It's just to illustrate the object from Hubble Space Telescope. Here on the left-hand side, that's an optical picture of a fraction of a globular cluster. Globular clusters are spherical clusters of about 1 million stars, which are held together by their mutual gravity. And these objects have been first detected around our galaxy, around our Milky Way. Our Milky Way has about 100 to 150 of them. They belong to the oldest objects known. They are already formed at very young, in a very young universe at the time of when our galaxy formed. So some people say these are the fossils of galaxy formation. They are typically more than 10 gigayears, more than 10 billion years old. And what we see when we observe them today is what we call an old stellar population. Yeah, so there are stars, 1 million stars, and initially they started with different masses, and then all these stars evolve. The massive stars evolve faster, and the low mass stars slower. I will get back a little bit to this later. And so the different colors here, they basically refer to the different evolutionary states of the stars. Yeah, so that is, and different masses also. And then what is here, this zoom in, this is an image taken with an X-ray telescope also from space, and we see that in the center of these globular star clusters we have a lot of X-ray sources, actually more than in the galactic field. Yeah, so there's an overabundance of these X-ray sources. And these X-ray sources are an astrophysical telltale sign for very compact binaries, typically a binary where one partner is a black hole or a neutron star, and the other is a donor, as we say. This is a star which donates mass to the black hole. An accretion disk is formed with hot gas, and we see this hot gas here in X-ray. So this is just to introduce to you the idea that in these globular clusters are interesting because we have an overabundance of binaries which have compact objects. Yeah, so that is already obviously, and that's the reason why already in this old paper there was a suspicion that there should be gravitational wave sources in globular clusters. At the bottom here, this I just sometimes show it. This is, let's say, our embarrassingly simple main or basic equation of motion, yeah, for all these stars, Newtonian, yeah, so the Newtonian for most of the particles, except a few exceptions, which I will come to. So this is just this summation, a direct summation of gravitational forces, Newtonian forces in this case, at some point where we are sitting, and then we sum up all the gravitational forces from all other particles. Asymptotically, it's an n square particle number, n square complexity. We can actually, certainly there are some long history of making this method faster, optimize it, do this full n square simulation as little times as possible, make long time steps, have different time step schemes, and so it is still optimized, but asymptotically from time to time we still need this fully resolved gravitational forces. And the reason is that our system is a gravothermal system, so there are actually transport effects, two-body relaxation, and so to some extent, we always need to take into account the graininess of the potential, and the degree and the time dependence of the graininess is important for the evolution. Yeah, so this is a whole topic for itself, and I will not go too much in detail. Ask me if you have some question about that. The second difficulty with this kind of systems and the simulations is that there is a very big trouble in small scales. In small scales, we have what we call 3-body or 4-body encounters. Here in the lower left is an example. It's just the traces of an encounter of one of these tight binaries, yeah, like they have been seen in the X-ray images, and have an encounter with a single star coming here from the top. And then there's a very energetic, in fact, chaotic encounter. There are signs of deterministic chaos in these encounters. And then the result of the encounter is typically that we get some eccentricity in the binary. The binary will be more strongly bound, and the single star carries away additional kinetic energy. There is a possibility still, so this is the deterministic chaos. On the other hand side, on the large scales, there is some averaging method so that we can say relatively reliably something about the global evolution of the systems, but there's always this interplay between chaos and deterministic evolution. And I think I will skip this now. I will not say more words about this, because this is just, again, in statements, this interplay between chaos on a small scale and large-scale deterministic evolution, and our simple equation of motion for the Newtonian case. And finally, for the introduction to the globular clusters, I think my final slide about the timescales which are at work here. I already mentioned that so the age of these clusters is comparable to the age of the universe with 10 to 10 years. Then there is this relaxation timescale. This is a timescale where 2-body encounters produce a phase mixing and a significant change of energies and also angular momenta of the stars in the cluster. This is of the order of 10 to 8 years. It's shorter than the lifetime. And the dynamical time is the typical orbital time. And then we have binary timescales which go from a year to months and days finally before they merge. And well, just, I mean, this is a little illustration. We have actually millisecond pulsars which rotate with millisecond period. This is not what we are resolving step by step. I mean, but there is some, maybe you could say, kind of subgrid physics included in our models for these millisecond pulsars. Yeah, in the systems, for another theoretical background, so these systems typically get very fast. With a dynamical timescale, they get into virial equilibrium, as we say, that potential and kinetic energy balance each other, like in a star, which is also in virial, the gases in the star is in a virial equilibrium. And then this virial equilibrium is perturbed by longer timescale, by this relaxation timescale. Yeah? So this relaxation evolution produces, for example, an increase in the central density, a core halo structure, and all of this certainly is important to understand why we have this overabundance of compact objects, compact binaries. Yeah, so that is, yeah, I think this was my background, and now I will jump a little bit into the history. So this is, I think, our first paper where we included relativistic dynamics in these generally Newtonian simulations. And in a later slide, I will just show the terms actually in more detail, which we take actually from published work. But it was in 2006. Gabor Kuppi, our postdoc, also Pow was involved in this work when he worked with me in Heidelberg. And we had already the idea that in this n-body simulation where we have Newtonian forces, we could see if we have a black hole and they come close enough together, a binary with two black holes, they come close enough together, so we can just add to the Newtonian acceleration the well-known post-Newtonian terms. And already in this paper, we just add all three actually. So not only, so what is it now? I mean, you are probably familiar with this notation that 1pn are the terms of dimension v square over c square, yeah? And 2pn is v4 over c4, where v is some velocity, yeah? Here it's written a, yeah, which is a little bit misleading, but I guess you all familiar about this. I mean, either we say the c is dimensionless, or we say this a2, this has a dimension of v square, yeah, and times acceleration. And here it's correspondingly v5 times acceleration. 2.5pn, this 1 over c5, is the term which leads to shrinking of the orbit and to gravitational wave emission. We were at that time not yet interested or did not yet publish anything about the gravitational wave emission, but we found actually that there is a runaway merger, a very commonly discussed phenomenon. If you have a dense enough globular cluster, there are several black holes forming, many black holes if the cluster is big enough. And in this plot, we have here the mass as a function of time in n-body time, which is roughly dynamical time. So 100 is of order of 10 to 8 years. This cluster, I think if I remember correctly, it was 10 to 5 or 10 to 6 solar masses. To be honest, I'm not 100% sure. And then we get actually by relativistic mergers of binary black holes, we get here the blue points are relativistic merger of binary black holes, and the mass here we have 1% of the total mass. Yeah, so that is 100. No, so, wait a second. 10 to 5. No, I think it was 10 to 5, 10 to 4, 1,000 solar masses, and here we have then one object which runs away and gets merger with more and more black holes and goes up to 5% of the total mass. Yeah, and this was interesting already at that time. No gravitational waves had been observed, but it was interesting in terms of the question, how do seed black holes form in the young universe, in young star clusters? And two things we still using actually in all papers up to now is that we implement this post-Newtonian forces here, yeah, with, or accelerations, as I put it here and put in question marks, in quotation marks, as perturbations in two-body CAS regularization. That's a long story. So the two-body CAS regularization is a special mathematical method, a transformation we use for tight binaries, tight Newtonian binaries, including Newtonian perturbations. And this regularizes the singularity of the two bodies, the Keplerian potential. Yeah, it makes it a harmonic oscillator. And this is very well behaved numerically. And so it was quite natural that we add also these post-Newtonian forces in this two-body CAS. And the two-body CAS actually does not require that the perturbation is small. It's more a technical, it's a technical term that we say perturbation because it is added to the two-body force in this special treatment. Yeah, but the perturbation can be large if we are close to the merger. And the method to switch it on actually inside, so there are some, let's say there are some criteria that when we have a binary which is sufficiently dynamically separated from the rest of the system, that means that the Newtonian perturbation is only a few percent of the two-body force. And then we are looking how much is the perturbation from the relativistic force, from the post-Newtonian force. And there are two criteria One is that the perihel shift actually by the Pn1 and Pn2 should be larger than 10 to minus 4 in radians, and the V over C should be larger than, so the speed larger than 10 to minus 3. And if these conditions are fulfilled, we always switch on, in this case, a full set 2.5 Pn. Yeah, so this was the status of 2006 of the paper. And then this paper I'm only mentioning for completeness or for historic interest. A few years later, there was already the growing interest in LIGO being built, and compact binaries in star clusters as gravitational wave sources. You see here the two titles. That was actually work done in the context of the Virgo Ego science community in Europe. And here we used not an n-body simulation, but a Monte Carlo simulation. We can later discuss a little bit the differences. It's kind of crazy n-body simulation, which is computationally very cheap, gives data similar to n-body simulations, but has a lot of approximations. And there actually we used for the binaries a similar procedure like we did in the previous paper. And this is a long story cut short, is now an old hat, so to say, but we already published, and I think it's quite often cited, that in these globular clusters, here we have the number of black holes as a function of time, here from 0 to 12 gigayear, a long simulation, and this is red and blue. I think this is difference, two models with different initial density, and we have order of a few hundred black holes in this cluster. And then we were also looking for the binary black hole mergers, which are in the expected frequency range of LIGO, and there is this magical 1 to 100 LIGO events per gigaparsec per year. That was the conclusion in this paper. And I think it is still roughly valid. I mean, now we have real measurements. And yeah, okay, I will keep it at that. So at this moment, or not at this moment, I mean, over the years now following this 2010 simulation, there was the question, how realistic is this? Can we really expect so many black holes? There were some detections, and people were not so convinced that there are really many black holes in star clusters. So one of my students in PKU, Long Wang, he got the task to start a really big full n-body simulation. So it means a million stars, many binaries already initially, and full astrophysics over all the time. It's 12 gigayears, which was before only done in the Monte Carlo simulation, not in direct n-body. And this is what we call the Dragon 1 simulation, just the long name kind of give inspiration for this name. And there's the 2015, 2016 papers, which give the numerical things, the codes, details, and the astrophysical results. And these Dragon 1 simulations, yeah, they were, the number of floating point operations needed is comparable to some of the largest cosmological simulation. It was a big challenge. Took many months. Every simulation took many months on a big supercomputer with GPU acceleration, many nodes. And yeah, so what did we get from it? A lot of astrophysical data, which is represented here in these black blobs in the middle, is how it would look, our simulated cluster, how it would look like in an optical telescope from the ground. Yeah, and we know now from our simulation, we know if the cluster looks like this, where are the objects which are more difficult to see in a telescope? Yeah, so maybe, okay, main sequence stars and red giants can be detected, that is the top here, can be detected spectroscopically. Giant branch stars here also, the AGB, but white dwarfs and binaries are actually much more difficult to see, yeah, by telescopes. And here there is this for us, not such a big surprise given the previous papers, but still was a kind of surprise for some people. We have actually, again, the order of over 100 black holes there, and many of them in binaries. Yeah? So these black holes, are potential LIGO Virgo sources. Yeah, so this we mentioned this already in this paper, but there was no quantitative analysis. But still, some I see here in the bottom, you see our LAHU supercomputer at NAOC and some gravitational waveform modeled from one of our merging binaries, but it was just more spontaneous. It's not in the paper. On the top here is for the astrophysicists. I will skip this now. So this is because when you look in a star cluster like this, yeah, this is the optical picture here in the telescope. A star cluster looks very boring. Yeah, so you always have a spherical system. Stars of different light intensity, more or less concentrated spherical blob. So the astrophysicists prefer this kind of semi-spectral presentation, where we put every star here in a coordinate system with a luminosity on the y-axis and the temperature, which is a proxy for color, spectral feature. The temperature here, high temperature on the left, low temperature on the right, and then the observed clusters like 12 gigayears, they have a typical signature here, of the main sequence and the giant branch, and it depends on time also. I will not go into details. It's just to see that our simulation reproduces the standards. And if we go in a little bit larger scale, we see also here the horizontal branch stars, which are going to become remnants, actually lose a lot of mass and then end up here. We see the white dwarfs, we see them here. We do not see the neutron stars and the black holes which form actually. Yeah, for this simulation, Longwang got a prize, an IAU prize, and also a bottle of whiskey by Douglas Heggie, who had put up a special award. And so this was a nice success. But yeah, so as I said, so with regard to the black holes and the black hole binaries and the gravitational waves, even though we had before developed this inclusion of relativistic terms, but we didn't discuss really very much about the black holes in these simulations. So in the next, for the Dragon 2 simulations, actually, which the papers appeared just 23 and 24 last year, one of the aims actually was to improve the relativistic treatment and get a better representation, or get a better idea what would our model star clusters produce for LIGO Virgo. Yeah? And so I have now here in this occasion between the Dragon 1 and Dragon 2, I have a few slides just illustrating what we are doing. Mainly, I think we are following here Luc Blanchet's algorithms. And as I said, it's nothing we invented. It is just what we are taking, and we can just we can look at the Post-Newtonian in the following way. Here on the top line, we have the acceleration, dv dt is just zero order. The 1 is for the Newtonian, and then we have conservative and dissipative terms, which are symbolized here with A and B. The conservative terms basically do not change the energy of the orbit. They just change the position of the orbit, the perihel shift, for example. That is what we have here in A, the two lowest order, the Pn1 and Pn2. And B actually is the dissipative term. In the dissipative term, we have also Pn1 and Pn2, which contain some energy change. And the gravitational radiation, it's a little bit misleading here. The gravitational radiation is always the 1 over c to the 5th term here in A and here in B. Yeah, so this gives the loss of energy. And this loss of energy can be also transferred into some waveform using very simple recipes like KIDA waveforms of 95. So this gives some key on the frequency, and simple waveforms also one can get from this. Yeah, so this is just an illustration when we do the tests of our terms, I mean, maybe for most of you is very well known. So we have here on the left-hand side is two black holes of 10 to 8 solar masses, and we have here in green the Newtonian orbit. It's an eccentric orbit where the center of mass is in the middle. And then we switch on the different terms. When we switch on the up to Pn2, c to the -4, we see then how the orbit moves around, gets a perial shift, and different from Mercury, we get something like 20 degrees per orbit, so just a huge perial shift. And here on the right-hand side, we can see how the orbit shrinks with every orbit, this is in our high-order time-dependent integration scheme. So this is just a predictor-corrector scheme where we typically integrate the Newtonian forces, and now we add these forces and follow this typically with 100 steps per orbit. That is roughly the way how this is followed. Already going back to this 2001 paper. Well, so now we are coming to LIGO, Virgo detections. This is just preparation or inspiration. I put this because we have one day visited also here in a meeting of the Virgo Ego science collaboration, visited this, and the huge vacuum tubes, and so I find this always impressive. But probably I don't have to tell most of you about this incredible engineering work and accuracy to measure and detect gravitational waves, what kind of successful effort this has been. And this is now the next step, we try now to see where are our black holes in this diagrams, which are here published, for example, by Alberto Cesana, where you see here the characteristic amplitude of gravitational waves as a function of frequency. Remember again the 1978, the old picture. Here the millihertz, actually 1 hertz and kilohertz. And so see, here is actually also the orbital time. We have 10 year, 1 year, an hour. And the red line is one example, so for one of our dragon black hole binaries. The other lines have been put in by Alberto already with some isolated analysis, just taking some binaries and see how they evolve. And we just put here one schematic line. This was one binary from our simulations, and it just was exactly here. And then we do not follow here the fast merger, so it merges. Basically, it starts in the LISA band, and it merges in the LIGO band. So that was already become clear. And so I think I will skip this. So the Dragon 2 simulations, so this is now the challenge for our Dragon 2 simulations. This is now the data we have today after LIGO Virgo has of order 100 plus events. And again, most of you probably know this plot. We read it here on the y-axis, solar masses. On the x-axis, this is just an arbitrary x-axis where we have put the most massive black hole merger detected by LIGO Virgo in the middle. This is here like, what is it, like 70 plus 100 something, merging nearly 200, like 180 solar mass merger product. And then we have here all the other guys, 2 objects, 2 black holes, blue points, the black holes, 20, 30, maybe 40 plus 50, becoming a 70, and so on. So we have here this statistics of events. There was one surprise for some people that we go so massive here. Yeah, so a single massive star evolution of massive stars in binaries did not yield such massive black holes in a binary. Yeah, so it's something like here the most massive one. It was for isolated stellar evolution. They had no idea how to form these guys. Yeah, and so now this is now I'm jumping to the Dragon 2 simulations, the results published in 3 papers. Actually, I think 23 are all of them have been submitted by 23, and I think 2 papers have appeared in 24. The first author is my former Humboldt fellow in Heidelberg, Manuel Arcazeta. He has been our team member and so to say the next important person after Long Wang did this Dragon 1. So Manuel Arcazeta is linked to the Dragon 2 simulations, and he is now a professor in GSSI Institute near Rome. And yeah, and he did actually 19 models, 19 different n-body simulations. Dragon 1 was only 4, up to 1 million stars, again, many binaries, all the things. And there was a lot of astrophysics improved, both the classical massive star evolution, winds, final initial mass relation, and so on. I will not go into details here. And also one important thing has been added now to these new simulations, that is to have a proper kicks for the merger product. Yeah, if 2 black holes merge, they get a relativistic kick due to the asymmetry of gravitational wave emission. And again, for this kick, there are some models, some papers. I have one slide also in the next slide. And so we use this kick, and that is important because of the retention fraction. There are some black holes kicked out of the clusters compared to the Dragon 1 simulations. So that's one thing, the astrophysical and the relativistic improvement. And the other thing is here, this is an example. So we get many black hole binaries, also massive. And in this case, we have here an evolution. This is a time evolution you see here from a few mega years vertically down to 200 mega years at the bottom. We start with already 2 massive binaries. They explode, they form, the first compact object is forming here, common envelope. We have a first massive black hole here at 3.7, yeah, 95 solar masses. But if it would be isolated, yeah, the partner is lost actually because of the loss of binding energy in the context of the mass loss. Yeah, so there would be no massive binary formed. What we need is actually 2 of these objects, and in the star cluster, they are coming together in a high density, and they form a black hole binary. And then we have 2nd and 3rd generation black hole binary mergers, and they lead at the end to something here. This object was selected to be most closely to the most massive LIGO-Virgo merger. Yeah, 95 and 95 give 191. Yeah, so this is for us is no surprise. We can get such massive objects, yeah, in our simulations. And here is actually the formulas used on the bottom, the formulas used for the relativistic kicks actually from, yeah, I forgot to put the original citation here. So the citation is in the Arcazeta papers. And there's one angle undefined because we did not include the spin yet from the astrophysical massive star evolution. That is something for the future actually. Yeah, and now here's a counterpart of what you have seen before from Alberto's paper, where I put just this one line. And now we have from the Dragon 2 simulations, we have here the evolution of all our binaries in the diagram here, going from millihertz LISA to LIGO. Desigo also here in the middle. They start eccentric actually, and sorry, they start eccentric, then become nearly circular and then go over here in the LIGO Virgo. And then we don't follow the final merger. Actually, we just let them merge in the time scale is of the order of a few days, I think. Yeah. And yeah, and this is the kind of the most interesting result I like to show for this from this Dragon 2 work. That's actually from all our models, the different star cluster models, a plot of all the mergers in a diagram where we plot the mass ratio of the black hole, binary black hole mergers, mass ratio from 1 to small mass ratio. And this is the mass of the primary on the x-axis, 10, 100. And so the colored points are all the mergers we get in our simulations. The red area here is what is called the forbidden zone, where the isolated binary evolution has a trouble actually to get the objects. In star clusters, we have no problem to get these objects. Yeah. And in gray, underlying here in gray is the GWTC3 catalog, which there I showed the visualization a few slides before. So in general, our conclusion is we are quite happy. We get the physics modeling in our star cluster models is quite well and reproduces what we get. We have also 2 black hole neutron star mergers, but the statistics is too low. This is not yet, we have not yet analyzed this. We need to do more mergers for that. So I think, what about spins? I think that is now, it is very preliminary in a sense, actually, because we have done something, and there are even some published papers, some years ago, but this has not yet been incorporated in these complete astrophysical simulations of star clusters. Yeah, so for the Dragon 3, yeah, so the Dragon 3 is our future project. I think we hope to get a complete statistics also about the spin development of the objects. Yeah, but so what I will be showing you now is more like a little bit a mixed bag of different approaches which are there, but it is not yet continuous and all rounded up, you know, but just let's see. And then I think I will stop my talk. I think there's probably enough material, or maybe go only very quickly. Okay, let's go first what we are talking about. So what we are talking about is, again, this paper by Fay, Blanchet, and Bonanno is our basic reference, where we take actually, we take 2 things. Only one is here on the slide. One is the post-Newtonian effect of spin-spin and spin-orbit coupling, actually. And there are new PN orders. There is a 1.5 PN order here with C1 over C3, and there's a 2 PN for spin-spin interaction. Yeah, this is spin orbit. S is spin orbit. So spin orbit is 1.5 and 2.5, and spin-spin is 2 PN. So this is the order which was covered here in Fay, Blanchet, and Bonanno. And here's one example how it looks like. And there we have the spin vector of the 2 black holes. And in addition to that, in this paper, there's also an equation for the time evolution of the spin, ds1 dt and ds2 dt. But as I said, we have really not, it is included in the terms, actually, so it's in principle available, but it is not yet tested, not yet, how to say, digested for the big star cluster simulations. Yeah. But nevertheless, there is actually already some published work. And again, Pau, who has been also in our team, actually has been one of the important collaborators and co-supervisors of another student, Patrick Brehm, actually, who later also went to AEI in Potsdam. And Patrick already very early after we had this 2006, this dynamics up to PN 2.5 with Gabor Kuppi, So there was also, okay, let's put in this spin and spin orbit terms. And Patrick, in his master thesis, actually in the master thesis, he used very simple Kidder-style waveforms to produce waveforms for our spinning black holes. And we had, again, now we had these simulations with a few thousand black holes, very artificial, not a full mass spectrum. We get this runaway body, the massive black hole forming, and many mergers. And for some of these mergers now, so for all of these black holes, we give an initial spin. There were different variants, randomly or in one direction. And I cannot discuss now all the details. It also doesn't matter really very much, but just as a principle, so from one of these black hole mergers, we get here the gravitational waveform for the last seconds before coalescence. The first one is just an eccentric orbit with this modulation coming from the eccentricity of the orbit. And here below is a waveform where the two black holes have spins. Yeah, I just here I think two x and y, yes, x and y, perpendicular spins, and you see the spin orbit modulation of the gravitational wave signal. Yeah, so it was kind of a nice exercise to see. Unfortunately, as you know, the observed signals in LIGO Virgo are not yet good enough to give really such detailed waveforms. Yeah, it's just for how to say, as to visualize this fact. So this is a kind of game we did here in this old paper, and this is now many years later. Well, 3 years later, this was detected, but I think we are still far from determining spins from waveforms. Maybe with LISA, this will be better. And yeah, so this is here some tests also from the 2013 paper, actually, where Patrick actually followed. Now we have again one binary black hole. It is shrinking with its spins. The spins are interacting, and at the end we get a merger with a final spin. Yeah, and what we did here is actually, as a function of time in seconds, we have here the angular momentum in some dimensionless units. And this is the simulation of the black hole binary from using all our Post-Newtonian terms, how the total angular momentum goes away. And this is now at the time of merger, we have this. And the solid line, that is what a prediction by Rizzolla, yeah, some prediction, you give me a black hole binary with two spins, then I predict approximately, that is what Luciano Rizzolla did with full GR simulations, I predict you what is the final spin. Yeah? And the two curves just match here. So this is, to that extent, our conclusion was this Post-Newtonian is working quite well with spins. Well, I think I will skip this. This is about the runaway object. Again, we had this runaway black hole, and it had a spin now. So that's a generic spin of 0.3 was our result. Yeah, so that should be, if a runaway black hole forms in the early universe, maybe it should have something like a spin 0.3 if we take our simulations by the words. And here is also, as I told you, this is, I think, never published, but I show it many times in talks. This is how these post-Newtonian terms, what's the relative importance of these post-Newtonian terms, yeah, again, as a function of time. This is typically still a little bit away from the merger. We are talking here maybe about days or weeks of a massive black hole orbiting. And one would be the Newtonian two-body interaction. And then we have here the 1pn. So this is a modulus of the force. Yeah. So each post-Newtonian term, the 1pn, 2pn, and so on, can be, there's a vector, a three-dimensional acceleration vector, and this points somewhere, yeah, and we take the modulus and compare it, yeah. And so in that sense, the 1pn is, as one maybe would expect, the largest, and then we have here the 2pn, And there's already here the 1.5 pn spin orbit. Yeah, I think we choose the spin which gives the highest effect. Yeah, and here we have the wait a second, the 2.5 pn I think is the blue one, and this one is a 3 pn and higher. Oops, sorry. And yeah, we go down here the higher order terms, and yeah, so the 2.5 is the energy loss here, this one by gravitational wave. So this is about 1% here, yeah, so you can estimate where we are. And it should not be, you should not be confused, because, I mean, all these vectors have different directions, yeah. So the 1 pn typically is along the orbit, yeah, so it changes the pericenter, yeah. While the 2.5 pn is an energy loss, it's maybe more directed inwards, very, very roughly speaking. Yeah, so, but it is interesting. Anyway, yeah, I think I will go now very fast. We have already 1 hour. In preparation, actually, nuclear star clusters. Now, before I talked about globular star clusters, that these objects, spherical clusters, I told you about 150 are around the Milky Way, our own galaxy. Now, these are not the gravitational wave sources, actually. We now know that the universe is full of globular clusters. Nearly every galaxy has a lot of globular clusters. And some galaxies have not only 100, but thousands, yeah, and different ages. And even in the youngest universe now, some progenitors of globular clusters have been observed. And some of these globular clusters, as I told you, they formed intermediate mass black holes, and they start growing. And then if they go further, what we may get, but we have not yet done really the full simulation from the beginning to the end. So what is the end? The end is what we see today in galaxies, in centers of galaxies. We see nuclear star clusters, maybe 100 million stars which surround a very massive black hole, yeah, a black hole of millions or even 10 to 7 or 10 to 8 solar masses. Yeah. And these objects is what we call nuclear star clusters. So there is already the pre-existing supermassive black hole. Yeah. And we have not yet, as I said, we have not bridged this gap yet. But these nuclear star clusters, when they are there, they are another interesting source of gravitational waves. And there are, for example, there are issues like extreme mass ratio in spirals of stellar mass and intermediate mass black holes onto the supermassive black holes. Yeah. There are also normal black holes, like in our globular star cluster simulations, but all of this is still very cursory, and I will skip a few slides and refer 2 papers and then come to the wrap up, actually. So yeah, so this is about the nuclear star cluster in our own galaxy. Yeah, so this is a kind of sketch what we have in our own galaxy, and I already said it in words. So we have our galaxy, the Milky Way, yeah, with a size of 10 kiloparsec, 30,000 light years, and then we zoom in, yeah, so we zoom in here, and we come here to the size of 1 to 10 parsec. And there we have actually a star cluster, a dense star cluster here with millions to 10 to 8 solar masses per cube parsec. Yeah, this is a situation if we were on a planet in such a star cluster, the night sky would be bright like the sun. Yeah, it is an extreme stellar density. And inside, again, zoom in, there's this central black hole. In our case, our galaxy kind of few million solar masses. And here are some more zoom-ins from observations. I think I will skip this and only go to this one, which is now very well known. In the inner light days here, we have these stars which have been observed, how they orbit around the supermassive central black hole. And this is certainly, yeah, all our post-Newtonian dynamics can be used, yeah, but our goal is actually not just to simulate these 10 or 100 stars. Some people have done this, but we are interested in the astrophysics of the million or 10 million or 10 to 8 stars around and how the outskirts refill. There are some loss cones, some stars are absorbed by the black hole, and from outside these objects are refilled, and how the whole dynamics of such a nuclear star cluster goes on. And there's one published paper of 2019, which we call the Dragon 1 of the Galactic Center. Our Silk Road team member Taras Panamarev is actually one of the guys who did this. And I will only show one plot here from this simulation. This is after, I think, a few giga years. It's probably 5 giga years. After 5 giga years, we have here the stellar density from 10 to 7 to 10 to 2 solar mass per cube parsec as a function of radius. This is the scale here. I mean, from 10 to minus 2 parsec to 1050 parsec, and many different types of objects. But the interesting thing is a black line. These are the stellar mass black holes which formed in our simulation. Yeah, and some of them are in binaries. And at that time, we didn't have all the nice things from the Dragon 2 simulations. So we didn't follow the final in-spiral and the final evolution of the black hole binaries. This is now subject of future work. Next year, I have one new PhD student looking for this. Yeah. So this is one thing. And the other thing is, which is interesting, is nuclear star clusters which come from merging galaxies. Now, that's another field where we are working. It's also interesting in a cosmological sense. Yeah, the galaxies are merging. Here's the observational evidence, the antenna galaxies, so two galaxies just in the merging process. Here is some interesting case. Stephanie Kumosa detected this, where in X-ray, actually, we see two nuclei very close to merger, and it is assumed that both nuclei have a supermassive black hole. Yeah, so the and cosmology, the structure formation in the universe tell us that galaxies build up from bottom up, from small units to larger units. And here, this from Marta Volonteri, actually, this sketch illustrates that first the galaxies merge, and then each of them has a massive black hole. And for a short while, we have a black hole binary. And then maybe this black hole binary merges. And then in the next step, we have a binary. And there was a long time was a discussion, will they merge, or will there be multiple black holes kick each other out? And we have actually in our simulations, we have a long sequence of simulations where we implement the full post-Newtonian terms following these black holes, binary black holes inside the big star cluster. This is just a sketch how we set up the simulation, 2 massive black holes and a huge star cluster around. And then here some from the simulation now, not from the cosmological sketch, but simulation. We start with 2 galaxies. The density is, I think, the color code. Then the galactic nuclei come close to each other. Yeah, and this is already turned out 2012. And finally, we see here the black hole merging. And more interesting now, so we follow here, so this is 1 over semi-major axis of the binary, the supermassive black hole binary as a function of time. And we follow it with the post-Newtonian terms, how it contracts and merges, and also what kind of gravitational waves it emits. Here is the very old paper when we started this work. And the most recent citation is this one from 2022, where all the spin terms are included. And I promise it's really the last slide with content. This is a 2022 paper here by our Ukrainian team member, Margarita Sobolenko, with Peter Berczyk and several others in the team, where we follow the merger of this supermassive binary black hole, including spin, and have some model signal, which would be a theoretical signal for LISA. So this is all of the science I want to show. I will now totally skip the code and hardware. I'm happy to post the slides. So anybody interested, you can have a look or you can ask me. I will now go through all of this to the summary. But it's Peter Berzig actually in NAOC when we started our Lahu cluster in 2012. Actually, it was finished, and it was quite a remarkable system. And the only NAOC actually GPU technology in China actually enabled us to do this. And other supercomputers now, there's a new one in Finland. And now this is my summary message actually. And this is mixed actually. This is more the astrophysical thing. Yeah, so we get a good result for the LIGO Virgo sources, but we are still far away from a consistent picture. We need better statistics of all the globular clusters around in other galaxies. With regard to the post-Newtonian dynamics, the spin physics is not fully included in the big simulations yet. This is a future project. Another thing which I didn't mention is actually in some cases we get triples and quadruples, and how to deal with the post-Newtonian there is a tricky question. Some ideas, but not yet solved. And I think I took the slide away. Yes, so the Dragon 3 project actually, so this is how we call the next step, where we hope to tackle some of these questions. And I have two conference announcements, which I want to briefly here show, and then I go back to the summary message and for the discussion. So one is actually the IAU symposium on compact objects and binaries in dense star clusters. This will be held in Seoul, Korea, in June 16 to 20, 2025. You can find already a web page actually when you look for it, IAU symposium in Seoul. And there is also the Silk Road conference in Dali just after this IAU symposium. And yeah, I will go back here and thank you for your attention and questions, please.
I have a question about inclusion of post-Newtonian dynamics. You're talking about star clusters. Does it mean that you also have, I think this is your third bullet point, do you mean that you include the 3 and 4 body forces in your post-Newtonian calculations? I think
that's exactly, yeah.
Yeah.
That's exactly sorry, just I interrupted you. You're not.
Yeah, no, because I understand that at 1 p.m. there are 3 body forces, and at 2 p.m. I think there's up to 4 body forces. But I thought the 4 body force is not known.
Yeah, fortunately, actually, there are some very deep underlying theorems also for Newtonian dynamics of point masses. Mm-hmm. It's called the Sundman theorem, actually, which we say that always preferentially there's a 2-body correlation forming. Yeah? And so this is fortunately in these star clusters what we also see. We have actually, let's say, or how we start. We in the beginning, when everything is Newtonian, we have many triples and quadruples and interactions, and they kick out each other. But typically, when the object, when an inner binary of a multiple becomes very hard, very tightly bound, the 2-body force is dominating, and then we switch on the post-Newtonian. And it is very rare that a post-Newtonian object is perturbed by another one, in a sense that we have a true 3-body or 4-body relativistic object. It happens, and currently we have just not taken care of it, let's say simply. Yeah? So because we still more fighting with the spin implementation. What we are doing actually, that there's one thing, and it is not nice, yeah, but it's rare. What happens sometimes is a relativistic binary gets hit by a third object, and there is an exchange, yeah, and then we do a switching, yeah. So we have one relativistic binary, and if another single object hits, or also another binary, then we we just exchange the post-Newtonian. But currently we have only two-body post-Newtonian, yeah. So not the higher order. It can be done. I know I'm not really an expert yet in this, but it should be done. But it is rare, actually, very rare. Yeah.
I see. It's not necessary at this point. I think
I wouldn't say this because there are some of the most interesting objects, yeah, and about the growth of the massive body, you know, this could be interesting. Yeah, I wouldn't say it is not necessary, but let's say it's not on the top of the agenda currently. Yeah.
I see. Not a high priority because it's rare.
Yeah.
Because it's rare. But is there a chance that you can use it to test these 3 and 4 body forces? Because
yes.
Okay. Because I think it's from what I can tell is not tested very well, the 3 and 4 body forces in the post-Newtonian program.
Yes, actually I wish we are a small group, you know, and we had already some exchange with the Milan group actually, and they have some 3-body post-Newtonian and I think something tested for triple supermassive black holes, and in principle it's not a fundamental problem. We could include it because we have already in the Newtonian case we have some triple and quadruple detection, and the objects are already singled out, and it is possible actually. It just has not yet been done. Yeah.
I see. Thank you.
Jutta?
Thank you very much for this interesting talk. I have a question concerning the initial conditions that you use. So when you start these simulations, like these Dragon 1 simulations, and you have to assume some initial mass function. And this initial mass function, how much does it kind of then determine the end products that you get?
It has quite a significant influence. Let's say if you don't go to the very early universe, but just for standard star clusters around, there is observationally and theoretically some very well accepted fiducial initial mass function, which is called the Krupa IMF, which has actually is similar to the classical salpeter for high mass range, and for below a solar mass it gets a little bit flatter. It's just from observations this is determined, and we go from 0.08 to 150 solar masses initially now, and this is what currently most people use. We have the effect is strong because the massive stars they have a small number, but they determine the most massive mergers we get. And when you see in this diagram which I showed, we started already from very massive stars, from 2 binaries which have 100 solar mass stars, and then in order to get this most massive LIGO-Virgo merger. So this is important. If we have and we have some models, some people have proposed that in the young universe at very low metallicity we have top-heavy IMF, and then the frequency of black hole binaries and gravitational wave events, it will be totally different. Yeah. So therefore I'm saying when I showed this plot from the Dragon 2 simulations, that we get roughly a good distribution of mergers compared to LIGO-Virgo. Our conclusion was that exactly these parameters, the IMF, and also the models we have for how a massive star evolves, they cannot be completely wrong. So that was our conclusion. Yeah. So that's. Does this answer your question, or?
Yeah, it does. I imagine there should be quite some dependence, and yeah.
Absolutely, yeah.
Yeah. Okay.
It's less. I mean, the dependence is less. Sometimes there's a question also about the initial conditions with respect to structure of the cluster, the velocities of stars and things like that, there's a relaxation actually which flattens out many things, yeah, like initial fractal structure. Rotation could be important. That is very little explored yet, but it's important. Yeah, it has to have a look for the initial conditions. Yeah.
Yeah. Thank you. May I just add another question? Namely, can you learn something from these mergers in these globular clusters or in the nuclear clusters for the emergence of the supermassive black holes in the early universe?
Yes, not exactly. I mean, as I saw, so the Dragon 1 and Dragon 2 simulations were kind of tailored for the LIGO Virgo events, and this means we are talking about globular clusters in the 1 megaparsec surrounding. We have unpublished models, yeah, where we look for the very low metallicity, and there we get a much faster growth. So two things: lower metallicity and higher density, both higher initial density actually. So this plays a role. And we are just working on a paper which is close to submission, where we just increase, compared to the models I showed here, we just increase the density by a factor of 5, something like that. And suddenly we get, in a few mega years, we get actually 20,000 solar mass black hole. Yeah, it's very fast. And this could be progenitors in the very early universe, progenitors, seed black holes. Yes, so this is one interesting topic we are looking up with new simulations actually. So the current ones probably not exactly the topic, but we can learn something. Yes, in that sense, I could say yes.
But okay, I'm looking forward to your paper. Very interesting. Thank you.
Yeah, the other questions.
Maybe I can ask one.
Sure.
So you just mentioned that when you put when you have a higher density for clusters, you have higher merger rates in your simulations. So if I put a question in another way, like if I place two pairs of binaries of black holes, one in vacuum, the other in, for example, star clusters, and they have the same initial conditions. So, and what would be the difference between the waveforms of these two binary black holes during their merger evolution?
What was the difference between the two? I didn't get this actually. So,
and one pair is in vacuum, and the other pair is in star clusters.
There is no difference actually. That is exactly this issue with a preferred two-body interaction. Yeah. So most binary black holes decouple from the Newtonian dynamic in the final phase. Yeah. So in the final phase, let's say in the LIGO band, there is no difference. Yeah. When we go to LISA, when there is still this spin, yeah, so there are still some interactions with other stars can matter. So occasional disturbances, for example, but not in the LIGO band. There's no difference.
I see. Now, how can I understand the fact that when you have higher density in the cluster, then you would increase the merger rates and the event rates?
Yeah, this is an effect of also the merger rate is increased and it is faster, and we think this kind of very dense star clusters are not typical for the globular clusters we observe today. Yeah, they form from less dense progenitors. Yeah, so these highest density systems are typical for the early universe, and so there we get a faster growth and subsequent growth, which we have not yet modeled. Yeah, so how to go from 10⁴ to 10⁶ solar masses, we don't have a good model. We think it's not very difficult, but we don't have a good direct n-body model for that. Yeah. And another issue which is often forgotten, it is not that easy actually. You cannot infinitely increase the density and think you get more and more mergers. The problem is that when too many black hole binaries form, many binaries, they can kick each other out actually by Newtonian, first by Newtonian interaction, Newtonian 3-body and 4-body, they can kick each other out. And then later also in relativistic merger. So this is, or there's always a good sensitive choice of initial condition that I get a runaway merger rather than black holes kicking out each other. Yeah? So this is also not trivial issue.
I see. Thank you.
Maybe I can ask one question. So in
Yeah,
your
please feel
simulation,
free.
you haven't included the spin of black hole, right?
Yeah,
So far,
not in the Dragon 1 and Dragon 2 simulations. It has been included in these simulations of supermassive binary black holes, which I only very briefly mentioned at the end. And in the very old papers from 2013, where we didn't have a full mass spectrum of the star cluster. We just had an artificial system of black holes and stars only, you know, just of some equal mass. Yeah. But not in the big Dragon simulations.
I see. So let's say if you put an initial condition, the star or a black hole in the cluster, initially they don't have a spin, but when they go to the runaway merger and build out the final supermassive black hole, can the final supermassive black hole build out a spin or not?
Yes. So the spin can change. So the first thing is that we can actually assign a spin from stellar evolution models, but there are different models. So when the black hole forms, you know, there's Geneva model and a few other 2 or 3 choices. When the black hole forms from a massive star, what should be its spin? Yeah? And then we can give this spin to the black hole, and then it, by the spin-spin interactions, the spin changes, and then at the end, also at the final merger, we use this approximative formula to get the final spin of the merger. And this has been done for also unpublished. So we have actually, in order to test this, we have some simulations on the black holes, you know, 50,000 black holes, and just put 10% in binaries, and just to test all these spin mechanisms. And this is, in principle, it is working. But as I said, we have not yet systematically put this in the astrophysical models. This was just another master thesis, actually, of last year. One of my master students, just simulate this pure black hole cluster and put in all the spins. And this is like in 2013, like this old paper where we had a kind of toy model. But for the astrophysics, we need to now to put this naturally in the big star cluster models. And that is what will be the Dragon 3, I hope. Yeah, we are now working on it. Yeah.
Okay, it's very interesting because I'm also recently working on a similar thing. But I'm wondering if you start with the cluster without angular momentum, and the black hole in the cluster, they initially don't have spin, then how can they eventually get a spin in the final?
Well, there will be always orbital spin in a binary, actually. So the binary black hole, there will be always some orbital spin. And
but it's random, right?
Yeah,
if it's random. Binary, it's random.
Yeah,
so
it's random.
I would expect they will average it out.
Yes.
And then they will not necessary.
I think it will not average out because no, I think it will average out, yes, but the root mean square will not average out. Yeah, so the spin will the sum of the spins will be 0, but the root mean square, it means that all the black hole binaries which you have in a cluster, they have some spin actually. Yeah, so that is that is the conclusion from these pure black hole models. And then the more complicated question is when we start astrophysically, and clusters have rotation also. This is also one of the topics. We have some models with rotation, but too little, and there can be some net spin remaining, yeah, also for the massive black hole. But yeah,
It's something like a tidal torque interaction for other clusters.
Well, yes, if you are in a cosmological environment, there are also tidal torques, and yes, this is something we are totally neglecting, and we're looking more for the basic physics of the isolated star cluster. Except we may sometimes we throw two onto each other. Yes, but that's right. Yes, that is lots to do. Yeah.
Okay, thank you.
Any other questions? Maybe I can ask a brief one. Let's say we have not just have the supermassive black holes at the center, but also some intermediate mass black holes, and we have all the other smaller black holes, and they emit gravitational radiation. And for the intermediate mass black hole, we have this interesting case that even for stellar mass black holes, basically the gravitational waves, if we treat them in a bit more classical sense, are at this wave optics, geometric optics limit. Do you think when we have the gravitational waves kind of scattered or lensed by these intermediate mass black holes, that we could observe this on Earth with LISA or with other instruments?
I'm not sure whether I can give any comment. Really, I can say anything about that. I mean, that's you're referring to that intermediate mass black holes will work as lenses for gravitational waves from more distant supermassive black holes. Is that what you have in mind? Actually?
No, I actually mean also when we have, for example, our galaxy or Messier 87.
Okay.
When we have their intermediate mass black hole, we have the big one at the center there, of course, and we have stellar mass binaries. The gravitational waves are still roughly in the geometric optics limit. There we can still apply the geometric optics formalism, which is quite easy. But let's say we have also like more cluster which contains an intermediate mass black hole. And there, of course, there's this interesting fact that then scattering effects or wave optics effects become important. Do you think, maybe I can rephrase it, do you think the stellar mass black holes we have in
I'm not sure whether
I
can give any answer to this. I really don't know, actually.
The idea was basically when we have a certain number of binaries which in spirals still the gravitational waves fall into this intermediate mass black hole and then are scattered such that we observe them on Earth. Do you think we have enough black holes that we maybe also get some idea about like the frequency dependency of the scattering? So this may take us maybe a bit more about also strong gravity.
So this is, I mean, you are asking for in an intermediate mass black hole in a star cluster, and then other single or binary black holes nearby, near the intermediate mass black hole. Is this, I mean, just a scenario which you have in mind, or is the
a bit in this direction? I mean, it's more like if there are enough black holes, and then maybe we can observe some scattering effects, which tell us more than about the scattering effects on the strong gravity regime. Do you think this might be possible?
Honestly, I have no idea. I can't say. I haven't thought about this, and also, I mean, from different angles. Just astrophysically, I'm not sure what kind of conditions are exactly needed to have strong scattering. I think that all the observations are still. I mean, it's tough to observe objects at all. I mean, with LISA and LIGO and so, and I have really no idea. The other thing is also in our simulations, typically we have not bridged this regime between so I have told you about the current clusters where we mostly have stellar mass black holes, maybe go up to a few hundred. And then this very young star cluster where we have this seed IMBH forming, and we have not bridged the gap, so that that would be maybe interesting in your context, that we have already a 10 to 4, a 10 to 5 solar mass black hole, and then many other black holes around. And this is exactly what we are now also after following, actually, with the Dragon 3, also that we can say how many black hole binaries are surviving near the massive black hole, yeah, and they also get kicked out, actually. So there's an interesting question that the more dense these cusps are, where we have stars and also black holes, the more black holes will be kicked out, yeah, and how many are making it to make either an emery, and then there's also this Hills effect that they are disrupted, and so this is a lot of interesting scenarios. But so we are in the simulations, we are still not, we have not reached this stage, and from the theory of strong scatterings, I'm just not the expert. I really can't say anything, sorry.
Problem. It was more a curiosity question. Okay, are there any other questions? If not, then thank you very much for this nice overview talk. And with
Thank you.
that, we closed the official part of the seminar. And if there are more questions, you can ask them maybe without the recording.